Hello everyone, today I am going to discuss triaxial compression test. We can also call a triaxial test. So triaxial test has a many advantages as compared to direct shear test. Triaxial compression test gives us the more accurate result. So that's why we can use for the research work also to measure the shear strength of a soil. During the test we can measure the pore water pressure, or also we can measure the volume changes of a soil or a specimen. In this test, failure plane is a weakest plane. It means failure plane is not a fixed plane. We are not fixing the plane at the beginning of the test. Right? This test also we can perform for any kind of soil, for any type of soil, at any drainage condition also. Okay, so we can say triaxial test is very accurate test, we can say. So in the most cases we use for the research work because it gives the more accurate result. So let's discuss some of the triaxial compression test apparatus. So that is shown in the figure. So this triaxial compression test apparatus we can understand by a line diagram that is shown in the second figure. So this diagram, it consists of a circular base that has a central pedestal, and that pedestal has a one or two holes which are used for the drainage of the specimen. So two holes are given, you can see in the figure, and that is mentioned one or two. So these two holes are important for the drainage purpose or pore water pressure. We can measure the pore water pressure. Okay, and then cylindrical specimen generally of size 76 into 38 mm or 100 into 50 mm. So generally this size of this 76 into 38 mm or 100 into 50 mm are generally we use. So the specimen is placed on the saturated porous disc which is fixed in the top and bottom, you can see in the figure also, resting on the pedestal of the triaxial cell. Then after placing the specimen is encased in a rubber membrane. And this rubber membrane is sealed at the top with the O-ring. That is also O-ring is mentioned in the figure. So after placing the specimen, a triaxial cell is fitted to the top of the base plate with the help of three wing nuts. So three wing nuts is shown in the first figure. You can see in the first figure. Okay. Then you can see in the top side there is air release valve. So air release valve we keep open when filling the water. In the left side there is also oil valve. So oil valve we put some light machine oil in the triaxial cell to stop the leakage of water, to control to reduce the leakage of water. Okay, then loading ram is given. So through the loading ram we provide the load, we apply the vertical load on the specimen. So basically this triaxial test is performed in the two stages. The first stage is the consolidation stage and second stage is the shear stage. So what we do in the consolidation stage? So in the consolidation stage we place the specimen on the pedestal, central pedestal, and after that when we fitted the triaxial cell on the pedestal, so then that whole triaxial cell we fill with the water. So this water is apply all around the pressure on the soil. So this all around pressure is called a confining pressure, or generally we denote by sigma C. Are you getting a point? So we are applying the all around pressure by filling the water in the, we can fill the glycerine also, but generally we fill the water in the triaxial cell, so that a all around pressure is developed, and all around means on the periphery also, or on the top and the bottom also, there is a confining pressure is applied due to the water. So what we do after applying the confining pressure, we allow specimen to consolidate. We allow the specimen to consolidate, right? After the consolidation when over, then we apply a deviated stress. We apply some extra some stress through the jack, or which is fixed with this electric. We can operate by electric motor also, and by manual we can operate. So that deviated stress is applied from the top, okay, from the top. So on the top there is a two stress. The total stress will be confining pressure plus deviated stress. Are you getting my point? So that comes under the shear stress. When you are applying the deviated stress, that will come under the shear stress. So basically this test is performed in the two stages. The first stage is the consolidation stage, and the second stage is the shear stage. Okay. Deviated stress we generally denote by the sigma d. So that mechanism you can understand by drawing the free body diagram. What are the stresses acting on the soil specimen? So that you can understand by this figure. So this is the elevation of a soil specimen. So basically the soil specimen is a cylindrical shape, right? But we are making the elevation diagram, so it will show on that a rectangular diagram. Okay. Size is not mentioned in the figure. So when we apply the water, we fill the water in a triaxial cell, then it will apply a confining pressure, all around pressure on the soil specimen, and that is called a confining pressure. Do not confuse. And this confining pressure will act on the side of specimen and the top and bottom also. Sometimes we confuse how it will apply a confining pressure on the top and bottom. So it will apply a confining pressure on the top and bottom also. Okay. And we allow a specimen to consolidate. So this will come under the consolidation stage. When once consolidation is over, consolidation process is complete, then we will apply some deviated stress from the top, okay, and then it will apply a deviated stress on the soil specimen. So that you can understand by this figure. So see in this figure, so there is extra stress is comes, that is denoted by sigma d. Generally deviated stress is denoted by sigma d. And the total, whatever the total stress or coming on the top and bottom, that will be the major principal stress. That will be the major principal stress. So you can write also sigma d is equal to sigma 1 minus sigma 3. Where the sigma 3 is a minor principal stress. So in the side of wall of specimen, there is a confining pressure, there is a minor principal stress, so that will be equal. Sigma 2 is also a perpendicular to sigma 3, so that value will be equal, because on the side of the wall only confining pressure is there, okay. We can draw the plan diagram also. So see in the plan diagram there is I told you that soil specimen is cylindrical, so when you will see in the top it will show a circular. So circular, and the periphery of the stress which is acting on the periphery would be the confining pressure, or generally we denote by sigma c. So it means the total stress on the top of soil specimen will be sigma 1, that is major principal stress, and that will be summation of confining pressure and deviated stress. And the side, whatever the stress acting on the side of the soil specimen, so that is minor principal stress, we denote by sigma 3, that is also equal to the confining pressure, generally we denote by sigma c. So we can call, or we can say sigma c will be equal to the sigma 3. The triaxial test apparatus has some special attachments, and that we have to discuss all the attachments. That is very necessary, because of this attachment we can measure the pore water pressure, we can measure the volume changes, etc. Okay. So the first attachment we have mercury control system. So that is shown in the figure. So this mercury control system is maintained the cell pressure in the triaxial test. So you can see in the figure there is 2 limbs of mercury control system. and in which there is a mercury is filled. So the upper pot of surface of upper pot is open to the atmosphere, so gauge pressure is 0 because the gauge pressure is equal to the absolute pressure minus atmospheric pressure, right? So we can measure the pressure at the center of a specimen, or we can measure the cell pressure by using the theory of manometer. So what is the basic fundamental of to measure the cell pressure or by using the manometer? So we will select the 2 points in the manometer, and we will go from one point to the second point. If we are going the downwards, we will take as a positive, and if you are going the upward, we will take as a negative. Are you getting my point? Okay. So our first point is the surface of upper pot, and the second point is the center of specimen, that is h/3 distance from the datum. Okay. So let's start from the first point to the second point. So we can write this equation. So at the surface of upper pot, pressure is 0, so we can write 0, and we are going downward up to the height of h1. So we can write gamma W. So gamma M, that is unit weight of mercury, h1. Again we have to go upward at the surface of this lower pot in the middle of the mercury. So that is height h2 height from the datum. So we can write minus gamma M h2. Again we have to go upward, but there is not mercury, there is water. So we have to write unit weight of water. So that we can write h3 minus h2 into gamma W, unit weight of water. And that will be equal to sigma C. Sigma C the cell pressure, or we can say confining pressure. We can write sigma C is equal to gamma M into h1 minus h2 plus h2 minus h3 into gamma W. Okay. So by using this relation, we can measure the confining pressure, we can measure the cell pressure. So the other device, that is a pore water pressure device. You can see in the figure. So in this device, there is 2 things that are important. So there is a one null indicator. There is a null indicator. Null indicator, it means in which there is a mercury is filled. Okay, and this is showing the no flow condition. So in the null indicator, there is a flow condition is 0. There is no flow of mercury. Okay, and there is a 2 limbs attached through the null indicator. The left limb is attached to the triaxial cell, and right limb is attached to the pressure gauge or control cylinder, right? Okay. And there is also manometer is attached to this control cylinder. So what is happening, any changes is happening in the pore water pressure in the soil specimen, it will cause a change in the level of mercury in the null indicator. So if something happening in the specimen, it will affect the level of mercury in the null indicator. And null indicator is showing the no flow condition. So some pressure is applied by the control cylinder to maintain the level of mercury in the null indicator, to maintain the horizontal level of mercury in the null indicator. So whatever the pressure is applied by the control cylinder, there is also piston or control cylinder is filled with the water. So whatever the stress applied by the control cylinder, so that pressure is measured by the pressure gauge. So that pressure is we can calculate by pressure gauge or manometer. So that will give us the pore water pressure. Third device we have, the third device is attached to the triaxial cell, that is volume changes measurement, and that is very easy. So you can calculate the volume changes, is very easy. So one burette is attached to the triaxial cell. So whatever the volume changes in the soil specimen, so what volume changes because of the water is flowing out or flowing in, right? In some cases, in the case of dense sand, volume is increases. So why volume is increasing? So volume is increasing because of the water is going inside the soil specimen. So suppose whatever the volume of water is going out from the soil specimen, so that will be equal to the changes in the volume of soil specimen, and that volume of water will collect in the burette. So the volume of water in the burette will be increased. So whatever the increase is in the volume of water in the burette, that will give us the change in the volume of soil. Or in the over-consolidated case, in the case of dense sand also, whatever the volume of water decrease in the burette will be equal to the changes in the volume of soil specimen. So these two things are important. Maybe soil specimen may be increase, volume of soil specimen may be increase or maybe decrease. So that is we can calculate. So if the volume of soil specimen is decreased, so the water level in the burette will increase, and vice versa. So it has some merits and demerits of triaxial test. That is very important. So merit are control over the drainage condition. So that is a disadvantage over the triaxial test. Water pressure changes and volumetric changes can be measured by using those special devices. The stress distribution on the failure plane is uniform. So in the case of triaxial test, we have seen that we have taken the assumption that stress distribution is uniform, but that was not uniform. But in this case, stress distribution is uniform. A specimen is free to fall on the weakest plane. Means we have not fixed the failure plane. We have not fixed the weakest plane. Whatever the failure plane will come and will be weakest plane. Okay. Mohr circle can be drawn at any stages of shear, but in the direct shear test, Mohr circle we can draw only at the failure condition, at the failure stage. But in this case of triaxial compression test, we can draw the Mohr circle at any stage. The test is suitable for accurate research work because this gives us the accurate result, and that depending upon that accuracy we can use for the research work to measure the shear strength of the soil. Demerits also we can compare in other aspects, like apparatus is elaborate, costly and bulky. The drain test take a longer period as compared to that in direct shear test. So that direct shear test was a very quick test, we can say. The strain condition in the specimen are not uniform due to the frictional restraint produced by the loading cap and pedestal disc. So there is a loading cap on the top of the triaxial test. So that is connected with the loading ram. Okay, and ram is so designed in the triaxial test that it should have a less friction, or it does not permit the leakage of water, right? But we are assuming that friction is very less. Okay, but maybe it cannot be true. So that at that point there may be some type of some error we can get. So that is we can call a disadvantage of triaxial compression test. So now I'm going to discuss the computation of various parameters, and that is very important. So the first one is a post-consolidation dimension. So we perform the triaxial test in the two stages. First stage is the consolidation stage, and the second stage is shear stress. So what is happening when the consolidation process is over? Then dimension of soil specimen changes. Okay, it is not equal to the whatever the dimension was in the initial condition. So that is change. So we will find out. We will calculate what are the dimension of specimen after the consolidation. When the consolidation is over, what are the dimension of a soil specimen, right? So let us assume that Li, Vi and Ai is the length, area and the volume of soil specimen at the initial condition. L0, A0 and V0 is the length, area and volume when after the consolidation, right? I denoting the initial condition, O denoting the consolidation after the consolidation process, or O is denoting the 100% consolidation. Are you getting my point? Okay. So when initially volume was Vi, and after the consolidation process volume was V0. So what are the change in the volume? So we can write delta Vi is equal to Vi minus V0, right? We can also calculate the volumetric strain. So change in the volume divided by the original volume or initial volume, we will take as a volumetric strain. So we can write delta Vi divided by Vi. Right? Okay. For isotropic condition, we can write that linear strain will be equal to 1/3 of volumetric strain. So we can write this. Also we can write L naught is equal to Li minus delta Li, and we will put the delta I in the terms of linear strain. So we can write Li minus Li into epsilon L, or we can write L naught is equal to Li into 1 minus epsilon V divided by 3, where the epsilon V is the volumetric strain, that is equal to the 3 times of linear strain. Or we can calculate D naught also. We can calculate diameter of soil specimen, because the soil specimen is in the cylindrical shape. Once we know this value of L naught, so we can calculate also D naught from that relation, using this relation, without calculating the D naught using the above equation. So we can calculate D naught by knowing the L naught value. Once again I am repeating that Li, Ai and Vi is the length, area and volume at the initial condition before consolidation process, and L naught, A naught and V naught is the length, area and volume after the consolidation when the consolidation process is over, where the O is denoting the 100% consolidation. Right? We can calculate the cross section area during the shear. So second stage is the shear stage, in which we are applying the deviated stress on the soil specimen. Okay, or in that case, again this area of soil specimen changes, so we can calculate. So the volume of a soil specimen at any stage, we can write V naught plus minus delta V naught. What is the V naught? V naught is the volume after when the consolidation is over. And why we have written plus minus? Because it can be decreased or it can be increased. So whatever the increase or decrease, we have to take the total. So we have to write, in the case of suppose the volume is decreased, so we will write V naught minus delta V naught. In the case of when the volume is increased, in the case of denser or in the case of over consolidated clay, so we will write V naught plus delta V naught. So therefore we can write in terms of area into length. So what are the area? So we can write A into L naught minus delta L naught. Then A is the area of cross section at that point. Area of cross section of soil specimen at that point will be equal to the volume of a soil specimen at any stage or at any time. Or we can write A is equal to dividing both quantity, or we will take the we will take the V naught will common, then it will come like this. In the denominator we will take the L naught, it will come like this. We will write in the terms of volumetric strain or linear strain. So we can write like this. So L naught will be cancelled. So we can write A is equal to L naught into 1 plus minus delta V naught divided by V naught divided by 1 minus epsilon L. So this above equation is a very general equation. You can use anywhere during the test. Anywhere you can use. Okay. For an on drain test, as the volume changes, delta V naught is 0. In the case of undrained test, volume changes is 0. Volume is not changing. So in that case, volumetric strain will be 0 or delta V naught will be 0. So above equation will come like A naught divided by 1 minus epsilon L. This A, value of A is also called a corrected area. Okay. So in some book you can find there is written in AC, corrected area, denoted by AC. So A is showing the area, cross-section area of soil specimen at any stage, at any time, okay? Or A naught is showing the cross-section area at the initial condition for the shear stage. Means A naught is the cross-section area of specimen when the consolidation is over, right? There is a two stage, initial stage, consolidation stage. After the consolidation, there is a changes in the cross-section of soil specimen. There is a shear stage, okay? Third is one is the stresses. So there is a stresses, deviated stress, principal stress, and compressive stress or compressive stresses. So deviated stress we can calculate. So we are applying the some load on the vertical axis. On the vertical axis, and only this by using on the loading ram. Through the loading ram, we are applying the force. And that force is P. So we can calculate the whatever the stress developed by applied a force on the specimen. So whatever that stress developed, that is called a deviated stress. Or we can calculate P by L, where the P is the applied load and A is the area of cross section specimen at that point of time, at that stage, right? We can also write sigma D is equal to sigma 1 minus sigma 3. Sigma 1 is showing the total vertical stress developed on the top of the soil specimen, and sigma 3 is showing the confining pressure, confining stress, or confining or cell pressure we can say. So we can write sigma 1 minus sigma 3. Principal stresses. So in this case, major principal stress, that is sigma 1, will be equal to sigma 3 plus sigma D, or minus principal stress will be equal to sigma C, or confining pressure, or we can say cell pressure. Compressive strength. So the deviated stress at a failure, sigma 1 minus sigma 3, is known as the compressive strength of a soil. And that is very important. Okay? Sometimes you don't confuse, okay? Sometimes you generally confuse. So like, that compressive strength is the, like, whatever the strength, that is sigma 1. We are comparing with the major principal stress, but that is not a right. Okay? Because we are applying in the beginning, we are applying some cell pressure. Okay? So whatever the deviated stress is applied at the failure, that will be at the compressive strength of the soil. That will be as a compressive strength of the soil. Let's discuss some numericals. So the first numerical that we have, the following results were obtained from the series of consolidation and drain test on a soil in which the pore water pressure was not determined. So that is not given in the question. Determine the cohesion intercept C and the angle of shearing resistance phi. So these are the data given. Suppose you have performed the test on the three identical sample, we can say. And for the sample 1, there is a confining pressure 100 in terms of kilonewton per meter square, and deviated stress at failure in terms of 600 kilonewton per meter square. For the second sample is given, for the third sample is also given. Okay. So how we can calculate the cohesion intercept and how we can calculate the angle of internal friction or shear resistance? How we can calculate? So for calculation, C and phi, we have to draw the failure envelope. We have to draw the failure envelope on the tau and sigma axis. For drawing this failure envelope, we have to select some coordinates. Okay. So in this case, first we calculate the minor principal stress and major principal stress. So already we know that minus principal stress is equal to the cell pressure. So directly we can write minus principal stress for sample 1, 100. For sample 2, 200. For sample 3, 300, right? And major principal stress, that is sigma 1, is equal to the sigma D plus sigma C. So we can calculate sigma 1 is equal to 700 and 950 or in 1170. So that is in the kilonewton per meter square, right? Okay, so now we have the minor principal stress and major principal stress. So for every sample we have minor or major. So on the basis of minor principal stress and major principal stress, we can draw a Mohr circle. We can draw a Mohr circle. How we can draw a Mohr circle? First locate the two stress value on this tau sigma axis. Vertical axis is representing the shear stress and horizontal axis is representing the normal stress. Okay, these are normal stress in terms of total stress, right? Because the water pressure is not given, right? And the main important things we have to note by drawing the Mohr circle, that in the case of soil, the compressive stress we take as a positive, and negative and tensile stress we take as a negative. Okay, so draw the first circle for the sample 1, draw the second Mohr circle for sample 2, and draw the third Mohr circle and for the sample 3, and draw a failure envelope by touching all the circle, because this failure envelope, the location of that whatever the failure shear stress of the failure is giving for the same kind of soil, we have taken the 3 identical sample, right? So whatever the value of C and phi will give this, it will give for the same type of soil, right? So we will draw a failure envelope by touching all the circle. Okay. So this question you have to solve in the graph paper and with proper scaling. I have not made with the proper scaling, right? Okay. Or what you will find in the that graph paper, that when you are drawing a straight line, it not touches the all circle. So you have to find a correct one, like which failure envelope is representing the more or less accurate results, like. Okay. So whatever the intercept on the tau axis, that will give us the cohesion. Whatever the angle with the horizontal axis, that will give us the phi. So horizontal cohesion, that is 150, and phi, that is 24 degree. Okay. You try to solve in this graph paper also. Okay. Or in the graph paper, you just find what are the result. Okay. Presentation of result of triaxial test. So also we will discuss, you can draw the stress strain curve, you can draw the Mohr circle in the case of triaxial test. So that I am going to discuss. A stress strain curve is given for a drain test. So the first figure you can see, so the vertical axis is showing the deviated stress, that is sigma d, and it is written by sigma 1 minus sigma 3, so that is sigma d. Okay, and axial strain is placed on the horizontal axis, and deviated stress is placed on the vertical axis. So you can see the graph is shown for the dense sand over concentrated clay, or for loose sand normally concentrated clay. So in the case of dense sand, that first the graph is increasing, so the deviated stress is increasing, and then it's reached to the peak value, or then again when you are increasing the axial strain, then value is decreasing, and then it's become a constant, and finally it will give us the ultimate stress. So in the case of loose sand, when you are increasing the axial stress, the deviated stress is continuously increasing, and it reaches to the ultimate stress. So in the case of loose sand, we have not get any peak value. So what we do, we take the ultimate stress at the 20% of strain, right? Okay. The second graph is the B, that is given the volumetric strain. So for the dense sand, at the lower strain, the volume is decreasing, but at the larger strain, volume is continuously increasing. In the case of loose sand, volume is continuously decreasing at any stress, right? The second figure, that is figure 6, is given a stress strain curve for consolidated undrained test. So in this case also, that sigma d, that is the deviated stress, is placed on the vertical axis, and axial stress is placed on the horizontal axis. Graph is shown for the over concentrated clay, dense sand and loose sand. So that graph is similar to the that graph is shown for the drain test. So the test resistance curve for in the both cases are similar. So in the case of loose sand also we will take the ultimate stress value for the 20% strain. So you have to understand. Okay. So in the second, in the fourth figure, in the second figure, in the second one, so that is the graph is showing between the change in the pore water pressure between the axial strain. Change in the pore water pressure into axial stress. So this is the consolidated undrained test. So you can see for normally consolidated clay, when you are increasing the axial strain, then pore water pressure is increasing. But in the case of over consolidated clay or in the case of dense sand, where you are increasing the axial strain, then graph which first increases, pore water pressure is increases. But after when you are increasing the axial strain, pore water pressure is decreasing. The pore water pressure is giving the negative value. Means negative value means the pore water pressure is the less than atmospheric pressure. Pore water pressure is less than atmospheric pressure. Second is the B part, that is Mohr envelope. So how we can draw the Mohr envelope? In the Triaxial test also I have discussed about how we can draw. So in the case of Triaxial test, so for draw the Mohr envelope, so we have to do the test for 3 identical samples, at least 3 identical samples. Okay, so we will do the perform the test for 3 identical samples and we will get the minor stress or major stress for all these tests. Okay, and then we will plot on the sigma tau sigma axis. So this all these things you can see in the graph. So the figure number 7, that is shown in the failure envelope. In the case of effective stress, so Mohr envelope we can draw for the in the terms of effective stress or in the terms of normal stress or in in the terms of total stress. So in the first part I have drawn the Mohr envelope for the in terms of effective stress, where we are measuring the pore water pressure, and what we are doing, we are just deducting the pore water pressure from the total stress, and we are getting the effective stress, right? Okay. So you can see we have drawn the for this consolidated drain test. So this Mohr envelope. So we got the 3 Mohr circle, and we will draw the best more common tangent. Okay. So it should be, maybe it will not failure envelope will not touch the all 3 Mohr circle, but we have to draw the best one. Okay. So the failure envelope is crossing from the origin. So in the case of in this case, C intercept is 0 and the angle of resistance or angle of internal friction is phi dash. Okay. Or in the case of over consolidated clay, we have also drawn. So there is a cohesion intercept C dash and phi angle of internal friction is phi dash. So in terms of for normally consolidated clay, we can write shear strain is equal to S is equal to sigma dash tan phi. So we have not written C plus because in this case C0, we have not get any cohesion intercept. So we can write directly shear strength is equal to sigma dash tan phi. For over consolidated clay, shear strength we can write C dash plus sigma dash tan phi dash or phi. Why we have written the sigma dash? Because we are working in the terms of effective stress. We are working in the terms of effective stress. Then we have to write sigma dash. So the second one in terms of total stress, where we cannot measure the pore water pressure. So in that case, we can draw the Mohr circle in terms of total stress. So failure envelope for over consolidated clay, so that is shown in the figure. So this failure envelope draw for the consolidated undrained test. Consolidated undrained test. So that is why it is denoted by phi CU. CU means consolidated undrained test. CCU. Okay, so cohesion intercept CCU, or angle of internal friction phi CU, right? So again we can draw the failure envelope. So this first figure is compared with the total stress and effective stress. So see the total stress, when we draw the Mohr envelope with respect to total stress, so we got the lower angle of internal friction. When we draw in the case of effective stress, we got the higher angle of internal friction. Lower angle of internal. Sorry. Wait. Okay. So see, Mohr envelope we can draw for the effective stress in terms of effective stress, in terms of total stress. So this type of figure is compared with the effective stress and total stress. It doesn't mean that one circle is generated. Mohr circle is drawn for the 3 circle, but here is it mentioned only 1 circle, right? So in the case of, you can see in the figure, when failure envelope draw and the angle of internal friction is, in the case of effective stress, is maximum or more as compared to the in the case of normal stress, total stress, right? So for normally considered clay, CSN we can write S is equal to sigma 10 phi CU. 10 sigma we have written because this is the total stress. This is in terms of total stress, not effective stress. Phi CU, angle of internal friction for concentrated undrained test, CU. Similarly, we can write for over concentrated clay, CSN should be CCU plus sigma 10 phi CU, right? So these are the reference that I have taken. So for drawing the Mohr envelope, we have to do the test on 3 identical sample. So we can get the 3 for each sample. We will get the minor principal stress, major principal stress. For the second sample also, we have to find the minor principal stress, major principal stress, or by knowing the minor principal stress, major principal stress for all 3 identical sample, so we can draw the Mohr circle, and by drawing the Mohr circle, we can draw a failure envelope that is the base tangent on the all 3 circle. That would be the base tangent of all 3 Mohr circle. So these are the reference that I have taken. Thank you.